So our last speaker for the morning is Dan Roberts from Defio Labs, who will be telling us a bit about robust learning using Jacobian regularization.
Thanks very much. Thanks for inviting me up here to talk. My talk will be about a recent paper with the same title as my talk in a joint collaboration with Judy Hoffman, Georgia Tech, and Shoyeda, Facebook AI Research. So stability analysis lies at the heart of many scientific and engineering disciplines. In an unstable system, input perturbations can amplify and have substantial effect on the performance of a system. It's especially important to do a thorough stability analysis for complex engineering systems deployed in practice, lest there be catastrophic consequences, such as Tacoma Narrow Bridge collapse, the Challenger space shuttle disaster, or perhaps some future disasters that we may not be able to predict. It's, as a rule of thumb for robust engineering, it's important that your system be stable for both expected and unexpected perturbations, including adversarial perturbations. So for the context of this talk, I'm going to be focused on image classification, and in particular, the relationship between input perturbations and classification margins. So what do I mean? Here I've plotted the classification boundaries for a neural network trained on MNIST without any type of regularization. The black dot in the center is a test image, and then the circle represents distance along this plane to the nearest classification boundary. And this is two random out of the 28 times 28 different dimensions, two random directions are selected to give us this plane. So this is just a typical example of what classification boundary looks like. And in general, without regularization, these things tend to be sort of rugged and oddly shaped. I'll have more to say on that in a second. So for linear models, the relationship between, in general, if you have a small input perturbation, then that might shift the image, say, in a direction towards the edges of the circle. And if the perturbation is large enough, then the classification of the image might change, leading to adverse performance of the system. And so one way to combat this might be to try to increase the classification margins. For linear models, the way to do this has been known for a while. So L2 regularization, which is the second term in that equation, is known to maximize classification margin as well as reduce overfitting for linear models. So having L2 regularization has both this effect of increasing the classification margins and also reducing overfitting. And this has been a result that's been known for, I think, 20-ish years, 25 years. But it's not clear whether this continues to hold for nonlinear models. So in order to think about this further, we should consider what an input perturbation is actually doing to our model. So if we take an input image or input example, say x, and we apply a small perturbation epsilon, we can just Taylor expand the output function z, and the difference between the function's performance on the original input and the perturbed image is given by the input-output Jacobian, which is denoted J here. And this is just a simple Taylor expansion. So there's a connection between being able to be robust to small perturbations and the size of the Jacobian. And so a natural way then to reduce an instability to perturbations is to decrease the magnitude for each component of the Jacobian matrix. And another way of saying that is just by minimizing the square of the Frobenius norm of the input-output Jacobian. For linear models, this in fact reduces. It's a simple computation. You can show that this reduces to L2 regularization, but that's not the case for nonlinear models. So as part of this paper, what we propose is combining this Jacobian regularization term, or adding the Frobenius norm of the Jacobian to the loss function as an additional regularization. So L bar would be your supervised loss, say a cross entropy loss plus maybe any other regularization you're performing, like L2, and then we would add this additional term. And so first, here I have plotted the same plot that I discussed previously, which is this plot of, on the left, this plot of an unregularized, the classification margins for an unregularized model. And so if we just add L2 regularization, which is normally added in deep learning context for reducing overfitting, it doesn't really increase the classification margins. It has this effect of smoothing out the decision boundary, but it doesn't really make it any bigger. And there's no reason why we should expect it to be any bigger. However, for models trained with Jacobian regularization, which I introduced 2 slides ago, this has the natural effect of pushing the classification boundary out in a model agnostic way. And I'll discuss at the end of the talk how this improves robustness to different types of perturbations, both wide and adversarial, without hurting clean model performance. In the next few slides, let me just quickly explain how to efficiently compute the Jacobian regularization term that we introduced. So it's going to be 2 steps to digest. The first is the fact that any automatic differentiation system, as has been implemented in many packages that people use for training neural network models, can implements a function that computes that can compute the derivative of any vector as long as it's first contracted with another fixed vector. And so we can easily express the Jacobian in this fashion, the Frobenius norm of the Jacobian in this fashion, first by expressing it as a trace of the Jacobian squared, and then we can rewrite the trace in terms of a sum over complete basis of elements, which I've denoted E, and then we can use the formula for the definition of the Jacobian to express this as a derivative, and we can push the constant basis vector inside the derivative, and so we see that we can write this term as the derivative of a constant vector contracted with the output, the logits of the model. And so this is something that's very easy to compute. However, it has the problem that it scales with the number of classes that you're trying to classify. And in certain cases, for instance, a common data set that people use to test large-scale systems is ImageNet. There's 1,000 classes, so this is not very efficient. Instead, we can rewrite the Jacobian in terms of the expectation of an unbiased estimator, essentially that we can take advantage of the fact that if you average over a random unit vector, then that imposes a trace. And so there's a simple formula that lets us rewrite the Frobenius norm of the Jacobian in terms of the expectation over random unit vectors. And then combining these together, we can express the Frobenius norm of the Jacobian in terms of random projections. So this is the same formula on the previous slide, except we choose, instead of summing over the entire basis E, we are choosing random vectors V, and we can choose as many as we want, depending on how, in order to control the variance of our estimator. And in practice, you can set any number of projections equal to 1. I don't have time to show you how that performs, but it appears to be perfectly sufficient due to essentially the fact that you're getting a reduction in the variance from the size of the batch as well. Okay, so that's the definition of the algorithm. Let me just briefly provide some experiments to explain how this works. As I mentioned before, there's 2 types of noise that we're interested in. One is white noise, where we are sampling a we are sampling from a Gaussian with some fixed variance, some white noise, and then we add that to our input image, and then we crop the image to remain in the range 0 to 1, which is what we've defined as the valid domains of images. So this is one type of noise. A second type of noise is rather than random, where there's an adversary who's trying to find the shortest distance to change the classification of your image. So here's the famous example where you have a panda, and then you add what looks like complete white noise, and then the classifier changes to whatever target class you want it to change, in this case, a gibbon. And there's many different ways of computing adversarial images that's beyond the scope of this talk. But I'm sure in this audience everyone's familiar with this sort of thing. So let me very quickly describe two types of experiments, or I guess 3 types of experiments. The first type of experiment is to show that adding this regularization term doesn't have any negative properties on clean images, on clean models. Sorry, clean images. As I said in the beginning, for linear models, the notion of improving generalization and expanding classification margins are joined, but that's not true for nonlinear models. So we need to check that by pushing out the classification margins, we don't substantially hurt the performance of the models. And here, all the except for one case, all the experiments I'm going to show are on MNIST. In our paper, we did CFAR and also ImageNet. But it's simpler to just talk through MNIST on a version of Linnet. And here we have MNIST is either subsampled or the entire version of MNIST. We show no regularization, L2 regularization, dropout, Jacobian regularization are all combined. And one thing to see is that adding our Jacobian regularization doesn't substantially decrease the performance of the model on clean images, but it does substantially decrease the Frobenius norm of the Jacobian, which we should expect to have positive properties when dealing with perturbations. The same is true on CFAR 10. I'm going to skip this for time. And so just to show 2 quick experiments, the first is on white noise. We compare no regularization in black, L2 regularization in red, dropout regularization in green, and Jacobian regularization. We see that Jacobian regularization substantially confers robustness on the model, especially as we increase the magnitude of the white noise vector that we're adding. And I think we average over 5 different iterations. That's what the shaded part of the plot is. Similarly, we can test on adversarial noise, and here we compare against adversarial training, where adversarial images are added to the training set. We also compare Jacobian regularization, and we compare when we combine both of them. And in this case, we also see that Jacobian regularization confers substantial advantage against adversarial attacks. The attack we use here is the Carlini-Wagner attack, and we measure basically the distance to the closest adversarial image, and which should translate to the notion of pushing out the classification margins in the direction that's nearest if the adversarial attack is performed correctly. And I'm happy to describe the details of the algorithm for anyone who's interested. But this is probably the best way of finding adversarial images, and our regularization confers added defense against this sort of attack. And that's all I have. Thank you.
Hi, very nice. Do you have an intuition why increasing the margin doesn't hurt the performance?
Well, if you increase them enough, it does hurt the performance. I think that there's more plots in our paper and extensive studies in the appendix. I mean, if you increase the size of the regularization term substantially, then the performance will eventually degrade. One thing that seems to be true empirically is that over a reasonably wide range, there's a robustness. But I think probably the right way to think about this is that it's a tool that can be combined with other notions of regularization, such as L2 or dropout. It adds additional constraints to the model, so this can have adverse effects. Depending on the context that you want to deploy your model in, you should choose to push the margins out more or less. And I mean, it's straightforward what it's doing, and you can choose to use it as you see fit.
Yeah, thanks for the talk. Can you comment on the computational cost of this? Because it seems like by adding first-order derivatives to the objective function, performing gradient descent on this relies on second-order derivatives, right? So this might be costly in some cases.
So let me give you two explanations of why it's not costly. One is empirically, when we measured it on average, it seems to increase the computation cost only by 30%, so 1.3 times, like, I guess that's 30% works.
As in per gradient evaluation?
One second. And the worst we noticed was 2 times. But more importantly, what's happening is when you get the derivative of the vector contracted with a constant vector, that only costs you an additional backprop. So that's a constant speed up, and then times the number of projections. If you were not to use the random projections, you'd have to pay a cost of computing this for each class. So it would scale linearly with the number of classes. But if you use the random projection method, it only scales basically. It's basically order 1 is what I'm trying to tell you. But it's because you just basically are paying an extra cost of backprop, and that's it.
Thanks.
Thank you. Again, there is the list of results that show that adversarial attacks are in some sense inevitable in very high dimension. For example, the work of Adi Shamir and others that show you that whatever you do in the high dimensional representation, there's always a path that will take you from one category to another, which is relatively short, because the categories are actually closed. So, but there are problems with this type of results, because they usually assume that the perturbation can be unbounded in some sense. So I wonder, what exactly is your type of attacks here? I mean, it's a small magnitude noise to add it to the image.
I mean, we in our paper we tried the 3 different methods: the PGM method, the I forget, the one where you just take the sign of the gradients. I'm forgetting what the acronym for that is. And I think this Carlini-Wagner one is supposed to be state of the art. Essentially, you're asking, it solves an optimization problem that says, give me the smallest perturbation that causes the class to change. I think regardless of what those results are in high dimensional space, I mean, what's going on here is not. It's not a black box. It's straightforward, right? You're adding a constraint to the optimization problem, which says push out the margins. You might say that one thing you might say is that instead of the Frobenius norm, why not use the 1 norm, the L1 norm? Because it might be the case that on average all the components are reduced, but there's a particular direction where something's bad. That's a good point. The Frobenius norm does bound the 1 norm. You can both as an upper and lower bound. There's constants, and so maybe you worry about that. I think all I can say is that we know what it's doing. We're pushing out the margins. There still might be bad directions, but in general, it's on average pushing out the margins, and it seems to work well in practice, and it can be combined with other techniques.
Did you sometimes these adversarial defenses, they rely on gradient masking, so they evade attacks that involve looking at gradients and solving optimization problems on that network, but they cannot evade attacks from transfer attacks from other networks that don't have gradient masking. So did you try these transfer attacks to?
I'm trying to remember and also understand. You're saying you.
So let's say you flatten the landscape around the example, right? So optimization algorithms can't find a way out to the other class. But because adversarial examples transfer from one network to another, you can find an adversarial example for one network and then attack your network. And sometimes those attacks work when even powerful optimization attacks on your network would not work.
I don't remember whether that was one of the things we tried. I think that one thing to say is that we're not flattening. I don't think in the same sense, right? We're pushing out the boundaries, and so it might be the case that the mechanism is different. But I'd have to think about that more or remember whether we did that or not.
Any other questions? All right, let's thank our speaker one more time.